Have you ever wondered how we communicate with each other? How come you can listen to an Enigma talk and understand the complex ideas that the speaker is trying to explain? Have you wondered if we can replicate this process? So in this talk, I'll explain how to build a system that can learn to detect malware by reading and understanding the security literature. In security, many problems involve distinguishing between malicious and benign instances or activities. And nowadays, we often use machine learning for this problem, as we've seen in the first session today. Now, machine learning starts from some known benign and known malicious examples, and then tries to classify the remaining examples according to how similar they are to these initial examples. So, and we use this technique for detecting email spam, WhatsApp spam, phishing, malware, network attacks, for predicting which vulnerabilities are going to be exploited in the wild, which websites are going to be compromised in the near future, and probably many other security problems. And in all these problems, when applying machine learning, the key question is, what does it mean for two samples to be similar? And I'll illustrate this to make it clear. I'll illustrate it with two examples. So let's take spam. All right, so if we wanted to compare email messages to separate spam from ham, we could look at the words used in the body of the message, or we could look at features extracted from the email header, such as whether the message came from an IP address that is spoofed. Nowadays, on social media, there are many artificial intelligence bots, and it can be difficult for human users to spot that they're actually talking to an artificial intelligence. So if we wanted to apply machine learning to this problem, we could look similarly at their vocabulary. For the more advanced bots, we could look at the grammatical structure of their sentences to see if they use the patterns that are common. As you can see, there are many options here. Okay, and the process of choosing which features to use for a machine learning classifier is called feature engineering. This usually takes a lot of experimentation. It's done by data scientists who have specialized knowledge. So in our case, they know the security domain. And this can take many person months. It's a labor-intensive process. But at the same time, this process is key to the success of the machine learning project. And to illustrate why, I will show a third example, which will be a running example in this talk. And that is Android malware detection. So first, a little bit of background. Unlike traditional desktop malware, Android malware is a relatively recent phenomenon. It has some unique characteristics. For example, because the malware has access to telephony functionality, the SMS fraud is a common behavior. So the earliest malware detectors, Android malware detectors, compared apps based on the permissions that they required. And this worked well for a while. But as the malware evolved, these initial malware detectors became less effective. And that is because permissions reflect the privilege of the apps, but not their actual behavior. And also, if the malware includes a privilege escalation exploit, it doesn't actually need to request permissions. So then the next generation of Android malware detectors started looking at and Android API method calls, which actually reveal the malware behaviors. So this shows the importance of feature engineering, and in particular the fact that when we select features for using in machine learning, we must consider the threat semantics. And we do this using our knowledge of the security domain. But this knowledge is growing. So there is more and more information available about various security threats in academic papers, industry reports, blog posts. So for example, Google Scholar estimates that over 600,000 papers have been published on intrusion detection and over 100,000 on malware. So because of this, it can be difficult for humans to read all these papers and to assimilate all the knowledge that is potentially relevant. So here's our dilemma. This growing body of knowledge makes it increasingly more difficult to do feature engineering, but at the same time, we need good features in order to detect security threats. So we asked the question, can we turn this problem to our advantage? Can we build a system that engineers features automatically by mining security papers and extracting these features from the papers? In other words, can we create an artificial intelligence that can not only learn from examples, but it can also help us build other intelligent systems? So to do that, we need to understand first how security threats are described in natural language. So let's take a look at a couple of examples. This example says, the Z-Zone malware is designed to send SMS messages to certain premium numbers. Okay? So now, a security analyst reading this sentence would probably reach the conclusion that it talks about text messaging fraud. Right? But note that this conclusion is not based on purely linguistic clues. It is based on the analyst's knowledge that sending stuff to premium numbers can be related to fraud. The second example says the Ginger Master is often bundled with benign applications and tries to gain root access. So here again, a security professional reading this sentence would draw the conclusion that would know that bundling is a form of evasion, that gaining root access leads to privilege escalation. So as you can see, to understand what these sentences are saying, we must reach to the deeper meaning of the words. The Greek philosopher Plato explained this with an allegory of a cave where a group of prisoners is chained so that they can only see a wall their whole lives. And on this wall, they can see shadows of objects from the real world, but this is the only way they experience these objects. So now imagine that one of the prisoners were to leave the cave and then see the real world and then return to tell the other prisoners about it. Chances are that no matter what words he would use to describe the three-dimensional world, he would not be able to communicate with the other ones because they would lack a shared understanding of what the words mean. So a program trying to read the security literature is like the prisoners from Plato's cave. The words may have multiple meanings, so we must make sure that the program speaks the same language as the people writing those papers. So this is our first challenge, understanding the semantic meaning of the words used to describe security threats. And this is not just a challenge for our problem, for security. In the field of natural language processing, this is known as the common sense reasoning problem, and it is considered as one of the tough problems in their field. But we have another challenge here, which is specific to our domain. And I will illustrate it with this graph showing the number of unique words that appear in papers published in the IEEE Symposium on Security and Privacy, which is the leading research conference in security. So I'm interested to see how the cumulative count of these words changes over time. So what do you guys think? What does this look like? What should this look like? It increases, right? It turns out it looks like this, okay? So it grows at a constant rate, okay? So this means that each year, the new papers published include a constant amount of new terms that we must understand. And this is likely a result of the security arms race, where the attacker behaviors keep changing in order to bypass existing defenses. But this also means that we cannot use existing natural language processing techniques that map the text to predetermined categories of concepts. So instead, we must be able to discover behaviors, malware behaviors in an open-ended fashion. So to give you an example, an intuition for how we might be able to do this, let's take a look at how the researchers themselves describe the feature engineering process. So these papers typically have a section where the researchers would say, we look for API calls such as get device ID or get subscriber ID because these allow accessing sensitive data. We similarly look for other API calls that allow communication over the network and at API calls that allow executing external commands. So notice that the things that I have here on the left are concrete features that we can extract from an Android app using static and dynamic analysis tools. And here on the right, they are linked to abstract behaviors of the app. So these are the way a human would describe the kinds of things that we're trying to detect. So it seems that in order to understand these features and whether they are related to malware, we need to extract these abstract behaviors. So a behavior is a short description of malware activity, and for the purposes of this work, we consider it to be a phrase made up of a subject, a verb, and an object, where either the subject or the object may be missing. And we're gonna extract them by parsing the grammatical structure of the sentences. So if we go back to this sentence about ZZone, we are going to connect words with directed links that represent the grammatical dependencies between these words. We do this using existing tools called dependency parsers. And then from the types of these links, of these dependencies, we extract our subject-verb-object patterns. So here, for example, the first behavior that we extract is ZZone malware send SMS messages. And similarly, from this sentence, we extract two additional behaviors. So what this allows us to do is to take a long sentence and break it down into shorter phrases that each correspond to a single malware behavior. So now, using this technique, we can extract open-ended behaviors from the text, but we still don't know what they mean. So to find out, we are going to link them to concrete features. So when we see a sentence where a behavior, such as accessing sensitive data, is close in that sentence to a concrete feature, then we consider that these two are actually related. And this is based on an observation from cognitive psychology that whenever humans describe a concept, they tend to mention semantically related concepts at first, and then they mention increasingly less relevant terms. We similarly link the behaviors to malware, so we look for known malware families, as well as the word malware and its synonyms, and when we find these close to behaviors in the text, then we link the two. And this defines what is known as a semantic network, where the nodes correspond to security concepts. So here we have three types of nodes, malware families and concrete features, which are named entities, and behaviors which are extracted in an open-ended fashion, as I described before. And we link these nodes with edges. So an edge links two semantically related concepts. And we also assign weights on these edges based on the distance between the terms in the text, as well as how frequently they occur together. So this is an example. It's a fragment of our actual semantic network. So you can see we have the malware, the behavior, and feature nodes. We also have links between them. And note that some of the feature nodes cannot be reached from the malware nodes on this network. Right? So this suggests that they are likely to be not that relevant to malware detection. And another thing we do is we assign weights and we propagate them from the malware to the features. And this results in a ranking of the features. This tells us how relevant the features are according to malware detection, according to the papers we have processed. So this is how we engineer features automatically, and how we determine which are the features that are most relevant to malware detection. So now the question is, how well does this work? Okay, so we have conducted an experiment. We built a system called FeatureSmith that implements the techniques that I described before. We use this system to analyze a little over 1,000 papers. It found 383 features in these papers. But using the semantic network, it determined that only 195 of them are actually relevant to malware detection. And for a baseline, we're going to compare this against Drebin, which is a state-of-the-art Android malware detector. It is machine learning based, and it is the result of many years of research in the group where it was developed. And as a result of these years of research, it uses over 500,000 features. And these features include a list of 315 suspicious API calls. These are API calls that the researchers consider to be suspicious and relevant for malware detection, and this list was compiled manually. So to compare them, we trained two classifiers, one with the features that were automatically engineered by FeatureSmith, and the other one with the features used in Drebin. We use the same classification algorithm. We use random forests, the same corpus of benign and malicious apps for training and testing the classifier, and the same feature types. So we use Android permissions, Android API calls, and Android intents. And the goal of the experiment is to compare the effectiveness of the two feature sets in detecting malware. The first observation is that FeatureSmith discovers some new features that were absent from the manually engineered set, despite the fact that the manual set is so large. These are API calls that leak some sensitive information, and it turns out that they're actually used frequently by malware. And using these features, our classifier was able to detect one particular malware family that is a false negative for Drebin. And this illustrates the fact that human data scientists cannot assimilate all the relevant knowledge, and they may overlook some features that are important. So now, to compare the overall performance, I'm going to use this ROC plot, which shows the trade-off between the false positive rate and the true positive rate. So on this plot, the ideal operating point is in the top left, where we have 100% true positives and no false positives at all. And first, we're going to look at Drebin. We see that it comes pretty close to this ideal operating point. So the performance at 1% false positives is 92.5 true positives. And now, if we compare this to FeatureSmith, we see the performance is practically the same. So even though this system uses features that were created automatically by a program that processes the security literature, we can get a performance that is on par with a system that resulted from many years of research and uses many, many more features. For the fun of it, we also wanted to see how the knowledge evolves over time. So we trained classifiers with features extracted from papers published before 2012, 2013, 2014, and so forth. And we can see that in 2013, and we wanted to see what is the boost in detection performance that results from the additional knowledge published. So we can see that in 2013 there was a big jump, a big performance boost, and then in the subsequent years we kept improving, but we start seeing diminishing returns. I want to mention two alternatives to automatic feature engineering. So first of all, if you can enumerate all your features in advance, so let's say all the possible Android permissions, and you have access to a ground truth with labeled benign and malicious samples, then you can use a feature selection algorithm in order to determine which are the best features to separate the benign and malicious classes. Representation learning is another technique that discovers useful features from a ground truth, from a labeled ground truth, for example, by using a neural network. Now, unlike automatic feature engineering, these techniques are data-driven. So they identify features that are the best for modeling a given ground truth. And if that ground truth is not representative for the threat that you're trying to detect, then the features and the resulting models will also have those biases. And also, these techniques do not allow an automatic discovery of threat semantics. So in a nutshell, automatic feature engineering is a technique that allows you to discover semantically meaningful features by mining the natural documents written in natural language. It is able to discover some features that are missing from a carefully curated manual feature set, and it achieves a performance that is on par with that of a state-of-the-art malware detector. And I focused here on the Android malware detection problem, but I want to mention that this has many potential applications in security for detecting our AI bots, for threat intelligence, for intrusion detection, and in other fields. In fact, in the biomedical research field, the notion of literature-based discovery is well established. Nowadays, many people are afraid that artificial intelligence will replace humans in many activities. So I want to mention that I do not expect that tools like FeatureSmith will put data scientists out of a job. That is because, as we heard in the first talk this morning, human data scientists have intuition, and that is not something that we have yet figured out how to simulate. However, I do expect that a tool such as FeatureSmith will be very useful for these data scientists because it allows them to reason over the entire body of knowledge. So if you're interested, I invite you to go to featuresmith.org, download our paper, and we also made available our semantic network at this link. So now, taking a step back, I want to leave you with two thoughts. The first is that automated systems can understand the semantics of security concepts. And the second is that this is a powerful tool for creating attacks and defenses. So let's stop worrying about assimilating all the security knowledge available, and let's start working on tools that can discover this knowledge automatically. Thank you.
Sure.